This chart shows the standard model of particle physics, the most rigorously tested scientific theory ever created. It maps out the known inventory of the universe, organizing every basic building block of matter. This inventory is held together by the strong force. The math governing this force is called quantum chromodynamics, or QCD. It details exactly how quarks bind together to form the protons and neutrons inside every atom. When particles are smashed together at incredibly high energy levels, quarks spread out and act freely. In this high energy state, the traditional pen and paper math used to predict their behavior works perfectly. But at normal everyday energy levels, the strong force becomes overwhelmingly powerful and chaotic. This creates a severe problem. The traditional math completely fails at these normal energies. The equations loop into unsolvable infinities, leaving us unable to calculate the exact force that builds the visible universe. Physicists usually rely on perturbation theory, an approximation method that works when a force's coupling constant is small. But because the strong force coupling constant becomes incredibly large at low energies, the math breaks down. The root cause of this mathematical failure was an assumption about reality itself. The equations assumed that space and time were continuous, allowing particles to exist at infinitely small distances from one another. In 1974, physicist Kenneth Wilson proposed a solution. He reimagined continuous reality as a discrete mathematical grid, placing quarks onto a structured lattice. Chopping reality into a grid creates a firm boundary, or mathematical cutoff. By preventing particles from getting infinitely close to each other, the equations finally stop spiraling into infinity, making the strong force solvable. This is a visualization of Lattice QCD, translating the universe into a four-dimensional digital grid. Within this model, quarks are mathematically locked directly onto the intersecting nodes of the grid, and gluons exist entirely on the lines connecting those individual quark nodes. Instead of trying to analytically solve impossible equations, this rigid framework allows physicists to run simulations. They observe the chaotic behavioral relationships between particles based on known masses and energies. There is a major catch. Real space isn't a chunky grid. To get accurate physical results, the spacing between these nodes must be shrunk down until it approaches zero, a threshold known as the continuum limit. Calculating the interactions of every particle in an infinitely expansive universe is impossible for human minds. Solving this math requires a massive leap in physical technology. Moving away from these pen and paper theories, physicists turn to brute force, high-performance computing. Today, they rely on massive supercomputers powered by millions of GPU CUDA cores. CUDA cores are specialized processors that allow a computer to perform many thousands of calculations simultaneously. Originally designed for the complex parallel rendering of video games, these GPUs are uniquely suited for Lattice QCD. They easily process the highly repetitive Monte Carlo simulations, algorithms that use random sampling to predict outcomes, required to map the grid. This effort is massive. It takes teraflops of computing power running constantly for years just to accurately approximate the behavior of a single proton. All of this computing power is currently being aimed at a real-world physics problem, the recent muon G-2 experiment at Fermilab. During the experiment, physicists observed a discrepancy. Muons, which are heavier, short-lived cousins of the electron, displayed stronger magnetic properties than the standard model strictly predicts. This discrepancy leaves two possibilities. Scientists are either seeing a miscalculation of background noise, or they have found an undiscovered physical force pulling on the muon. To find out, scientists needed a theoretical prediction of how virtual quarks interact with the muon to compare against the physical experiment. Lattice QCD was the only tool capable of providing this exact baseline. Teams deployed the simulations across top-tier supercomputers in Germany and the US to map the particle interactions. The new Lattice QCD calculations aligned with the experimental findings. This provided critical insights into the muon's behavior, resolving the magnetic discrepancy without requiring a revision of the standard model. Lattice QCD converts continuous physics into a digital simulation. By assigning physical laws to a strict coordinate system, researchers can map subatomic movements with extremely fine time resolution. By trapping the strong force inside a digital grid, researchers can now simulate the conditions of the early universe and look for specific cracks in the standard model. Subscribe to The Explainer to explore more mysteries of the universe.